Hello everyone, my name is Deeksha. I am a third year student from BMS College of Engineering in Electronics and Communication. My project is Microwave Oven and it is based on embedded systems. To begin with, let me explain you what is an embedded system. As you are aware, an embedded system is a combination of hardware and software which is designed to perform a particular task. It is a small module in a larger system and it has one function which it performs in real time. Embedded system has its own features. 1. Dedicated functionality. 2. Real-time operation. 3. Resource constraints. 4. Compact form factor. 5. Low power consumption. And 6. Reliability and stability. An embedded system has a dedicated functionality because it is designed for a precise task such as controlling equipment, monitoring sensors, or processing data in real time. An embedded system has real-time operation, so it must be completed inside strict timing constraints to ensure well-timed responses and deterministic operation. An embedded system must consume low power because it is designed to function efficiently within power-restricted environments. An embedded system is known for stability and reliability. As you know, they are deployed in environments where failures are not acceptable as they can have catastrophic impact. These are the main key components of an embedded system. Let us look at them in detail. The main component is a microcontroller or processor. It is an IC, an integrated chip which is capable of being programmed to perform a specific task. The second main component is memory. An embedded system can have different types of memories, ROM, RAM, or hybrid memories. The next component is sensors, which detect physical quantities from the environment and convert it into electrical signals. Since the signals generated by sensors are of analog type, they must be converted to digital by using an analog to digital converter. This digital signal is then fed to the microprocessor or microcontroller, which can then process it. The next component is actuators. Actuators convert electrical signals into physical actions, for example, relays, motors, buzzers, etc. An actuator requires analog signal input to function properly. So, the digital signal which is generated by the microcontroller needs to be converted to an analog form by using a digital to analog converter. The analog signal is then fed to the actuator, which can continue its operation. And power supply is connected to all the components. The next component are the communication ports, which are used to transmit data between the microcontroller and other peripheral devices like memories, sensors, etc. This is a high-level block diagram of an embedded system. As we saw, an embedded system consists of hardware components as well as software components. The software is executed on the microcontroller to coordinate and control the hardware components. The software defines how the system reads the sensor inputs, processes the data, and makes decisions and drives actuators in real time. The most common programming language used to implement this logic in embedded systems is C. The C programming language is a general-purpose procedural programming language, and it is known for its high performance, portability, and efficient memory management, making it ideal for embedded systems development. C is considered a mid-level language because it combines high-level constructs such as functions and data types with low-level features like pointers that allow direct access to memory and hardware registers. The C language is thus slightly closer to the hardware, and this makes it efficient for controlling embedded systems. C has modular programming, including source and header files, and the conditional and looping constructs it provides can help us define the program logic, functions, and pointers efficiently. The use of preprocessor directives improves the code readability and ease of configuration. There are different types of embedded systems: standalone embedded systems, real-time operating systems, network embedded systems, and mobile embedded systems. Standalone embedded systems operate independently without a host computer. They do not need any control from an external host computer, and they simply process the input they receive from sensors or switches and produce the output via displays, LEDs, or motors, etc. Examples are washing machine and microwave oven. Real-time operating systems are those systems which must respond within time constraints. There are three categories: hard real-time operating system, soft real-time operating system, and firm real-time operating system. Hard real-time operating systems must meet the deadlines to avoid failures, and any delay in the response may have catastrophic impact. Soft real-time operating systems are those which can have some delay in their response, but the performance does not, but it's acceptable, but the performance degrades. Firm real-time operating systems are those systems where late results are unacceptable, but they do not have catastrophic failure. The next type is network embedded systems, which are connected to the network and to the internet and communicate across the network and share their data. Examples are smart home devices, network printers, IoT devices, etc. The last embedded system type is mobile embedded systems, which are designed for portable devices and are optimized for low power consumption. They are usually battery powered, compact, and energy efficient. Examples are smartphones, wearable devices such as smartwatches, etc. These are the stages of the project I followed for the microwave oven. The objective was to develop a microwave oven with 4 modes of cooking. The requirements were that the user is enabled to select the mode, he can set the time and temperature, and can also start, pause, and stop the cooking. In the design and components, I have made use of the PIC controller, and its included peripherals are matrix keypad, timers, CLCD, and fan. Following that is the implementation stage, where the logic was defined, and the final stage was the demonstration. The objective was, as I mentioned earlier, to develop an embedded microwave oven system by implementing multiple cooking modes with user interaction, timing control, and display handling. There were 4 available modes: micro mode, grill mode, convection mode, and start mode. The user is enabled to set the time and temperature through a keypad and display in a microcontroller board simulation software. There are a few hardware and software requirements for the project. The hardware requirements are PICSimLab. PICSimLab is a real-time emulator of development boards that provides integration with integrated development environments for programming the boards. It supports microcontrollers like PIC controller, AVR controller, etc. Software requirements are MPLAB X IDE, which is a proprietary freeware IDE from Microchip Technology, and it enables us to develop embedded applications on PIC microcontrollers, supports code editing, compiling, and debugging. The second software requirement was the MPLAB XC8 compiler, which is a C compiler that optimizes and translates the C source code into efficient machine language. Let's go into detail into the modes of operation. The powering on screen is displayed when the microwave oven is first powered on. It displays a welcome screen. Following that, it displays a menu screen with the 4 different options: micro mode, grill mode, convection mode, and start mode. The first mode is the micro mode, and to enter it, key 1 needs to be pressed on the matrix keypad. The next screen shows the power consumed by the oven. After 3 seconds, the user is prompted to set the time in minutes and seconds. The start button is used to reset the field to 0, and the hash button is entered to start the cooking operation. It then displays the remaining time on the display, and after completion, it displays a final screen that says time up, indicating that the cooking operation has completed. The second available mode is grill mode, and key 2 is pressed to enter the grill mode. The user is prompted once again to set the time and in minutes and seconds, and he can press start to clear the field and hash to enter the cooking operation. The next screen displays the amount of time left, and once completed, it indicates that the time is up. The third mode is the convection mode, and the key 3 is pressed on the matrix keypad to enter the convection mode. The user is then prompted to set the temperature in degrees Celsius, and pressing star clears the field, and pressing hash enters the preheating mode. The next screen that's displayed is the preheating mode, and it shows us how much time is left for reaching the desired temperature. On completion, the user is prompted once again to set the time for the actual microwave operation. Pressing hash enters the start operation, and once completed, the time up screen is displayed, indicating that the cooking operation has completed. The final mode is the start mode, and we press key number 4 to start the operation. The default time is set to 30 seconds, and the time left for cooking is displayed on the screen. There are 4 different options available for control during the process. Start mode is selected by key 4. This adds 30 seconds to the cooking time. Pause, which is selected by key 5, which pauses the cooking. And stop, which is selected by key 6, which stops the cooking. In case the microwave operation is paused, then the key 4 can be selected to resume the cooking. When the cooking is completed, the time displayed is 0 seconds, and a new screen is shown indicating that the time is up. Let us go into detail which are the components used for designing the project. I have listed out the different components used and their characteristics. The first component is the microcontroller board. The board used here was the PICSimLab PICGenius board. It is a versatile development tool designed for prototyping, and it features on-board peripherals like the CLCD, the matrix keypad, the fan. It supports the PIC16F877A microcontroller. The key features and specifications are listed out over here. The board contains the main microcontroller, which is the PIC16F877A microcontroller. It is a 40-pin microcontroller. It contains memories like flash, RAM, and EEPROM. The clock is typically a 20 MHz crystal oscillator. It contains peripherals like input and output, which are 8 logic input switches, which are displayed here, and 16 LEDs. It is connected to a 4x16 character LCD, CLCD, and 4 7-segment displays, although we are only making use of the CLCD displayed over here in this project. The interfaces provided by the board are a 4x4 matrix keypad and a piezo buzzer. The board also provides analog sensors, which are a potentiometer for analog input and an LM35 temperature sensor. For communication, the board makes use of USART and a USB 2.0 interface. The board is programmed by using onboard ISP, which is an in-circuit serial programming. However, since this microwave oven is simulated, we will only be emulating the board in PICSimLab. And the development environment which is used for controlling the board is MPLAB XID along with XE8 compiler. Let us look at the peripherals I have made use of in this project. First one is a 16x4 CLCD, which is character liquid crystal display. The CLCD is a 16-pin peripheral on the PICS16 F877A board, and it enables us to display characters on an LCD. It supports 4 lines of 16 characters each. The key pins are the power supply pins, the RS pins, the read-write pins, the enable pins, and the data or instruction pins. The power supply include the VDD pin and the VSS pin. The RS pin, which means register select, is used to indicate whether the signals transmitted to it is data or an instruction. The read-write pin is connected to ground by default in the board, so the default operation is writing to the LCD, which enables us to send data to the CLCD, which will be displayed on the screen. The enable pin allows us to enable the CLCD only when required. The data pins D0 to D7, the data or instruction pins D0 to D7 are used as and when required. There are 2 modes of operation for the CLCD, the 8-bit mode and the 4-bit mode. In the 8-bit mode, all D0 to D7 pins are used. However, in the 4-bit mode, only D4 to D7 pins are used. And this is usually used when there are insufficient pins on the microcontroller. When powered on, the initialization instructions are transmitted to the CLCD to set the required mode of operation. The next peripheral I've made use of is the matrix keypad. A matrix keypad is made up of buttons arranged in rows and columns. Each button sits exactly where a row and column cross each other. This diagram shows how the wires inside a 4x3 matrix keypad connect each row to each column. The matrix keypad makes use of a technique known as keypad scanning. This is used to detect which button is pressed on the keypad. The process of scanning is described here. First, the row lines are set as outputs and the column lines are set as inputs. Next, the pull-up resistors are enabled on the column lines, which ensure that the columns normally read as high. If something connects a column to the ground, that column will read as low. The microcontroller that sends a low signal to one row at a time while keeping all the other rows high. Then it checks each column to see if any of them have also gone low. If both a row and column are low at the same time, it indicates that the button at their crossing point has been pressed. This scanning process is done very quickly and is repeated for each row in turn. This way, the microcontroller can catch any key press almost instantly. The next component I've used is timers. The PICS16 F877A has a 20 MHz crystal oscillator which can be used to keep a track of time. The timer too is leveraged, which sets off an interrupt service routine to handle the time. Whenever the timer is set in the microwave oven, an interrupt is triggered which runs for the duration of the time set. A count variable is incremented for 20,000 times to indicate that 1 second has lapsed. The last component I've made use of is the fan, which is turned on and off as and when the microwave is carrying out its operations. Coming to the implementation, the main ports which are used for controlling the peripherals required in the project are listed here. Port B is used to set the columns of the matrix keypad as inputs. Port C is used to control a fan, specifically the RC2 pin is used to control a fan. Port D serves a dual purpose, to transmit data or instructions to the CLCD, as well as setting the rows of the matrix keypad as outputs. The lower nibble RD0 to RD3 is shared with the matrix keypad rows, whereas the upper nibble RD4 to RD7 is connected to the CLCD in 4-bit mode. Port E is used to set the CLCD control signals, register select and enable. The operation of the microwave oven is described here and how it was implemented. The microwave oven operation is implemented using states controlled by screen flag, and each value of the screen flag represents a different operating state, such as power on screen, menu screen, cooking mode selection, setting time and cooking operation. The timer 2 is configured with PR2 equal to 250. PR2 is a preset register and it generates frequent interrupts. A software counter inside the interrupt service routine accumulates 20,000 interrupts to represent 1 second. To set the timer 2 raises an interrupt by turning on the timer 2 interrupt flag. The control is then passed to the corresponding interrupt service routine, which keeps a track of time and updates the minutes and seconds. Once the timer reaches 0 seconds and 0 minutes, the ISR is terminated and the timer 2 interrupt flag is turned off. The microcontroller then returns to normal execution state. The matrix keypad operation consists of keypad scanning and key detection using state triggering. State triggering indicates that the key is detected only once and not continuously as it's being pressed. The fan is used to indicate cooking. Let me now give a small demonstration of the project. As I mentioned earlier, the project was implemented and simulated on PICSimLab, which is a development board emulator tool. I have selected the PICGenius board and the PIC16AF877A microcontroller board. I have already loaded the hex file which was generated. The hex file was generated by MPLAB XIDE, which was the integrated development environment that the code was developed in. The hex file generated has been loaded here, and as we can see, it displays the powering on screen, powering on microwave oven, and it then shows me the 4 available modes for cooking. 1 for micro mode, 2 grill mode, 3 convection mode and 4 start mode. I can select key 1 to start the micro mode. It displays the power being consumed by the microwave oven, which is 900 watts, and asks me to enter the time. I can enter 12 seconds. I can press the star key to clear the field, and I can enter it once again. Let's say 15 seconds. I can press the star key to start the micro mode. As you can see, the fan has started operating, indicating that the micro mode is in progress. The timer count has already started as well, and once it reaches 0, it displays that the time is up, indicating that the cooking process has completed. It returns to the available mode screen, the 4 available mode screen. I can select key 2 to start the grill mode. It prompts me to enter the time. I'm entering 12 minutes here, and I can press this hash key to start the grill mode. As you might have noticed earlier, there are 4 options available here in the screen. The timer has started down counting, but apart from that we have 4 options, which are 4 to start or resume, 5 to pause, and 6 to stop. When I press key 5, the operation stops, is paused for a while, and I can resume by pressing key 4. It resumes and it starts where it stopped. I can press key 6 to stop the complete operation. It indicates that it stopped and it returns to the menu screen, displaying the 4 available modes of cooking. The third mode available is convection mode, which can be selected by pressing key 3. Let me select that. It now prompts me to enter the temperature. Let me try to add 120 degrees Celsius. And again, I can press the star key to clear the value, and I can press hash to continue. It has entered the preheating screen, and it's displaying the time remaining as 54 seconds right now. Let me wait for the preheating to complete. The microwave oven has now finished preheating, and it now prompts me to set the time. I have set the time to 5 minutes, and I can press enter. I can press hash key to enter. The fan operation has started, indicating that the cooking mode, convection mode, is in progress. I can once again press 5 to pause the operation, and I can press key 4 to resume, and I can finally press key 6 to stop the operation. It indicates that it's stopped, and it returns to the menu screen, displaying the 4 available modes of cooking. The final mode available is start mode. I can select that by pressing key 4. The default time set for start mode is 30 seconds, and as we can see, the time right now is 22 seconds left, and the fan operation has started as well. I can press key 4 to add 30 more seconds to the time. So as you might have observed, it changed from 12 seconds to 42 seconds, indicating that 30 seconds have been added. The same functionalities of pausing and stopping are implemented here as well. I can press 5 to pause and press key 4 to resume. I can press key 6 to stop as well, and key 4 adds 30 seconds to the cooking time. Let me wait for it to complete. After completion, it displays a time up screen indicating that the cooking has completed. Okay, we can see that time has turned 0 and time up is displayed on screen. It finally returns to the menu screen, displaying the 4 modes of operation. And this was a small demonstration of the project. Thank you.